Now we have another video on Dr. White's fun with graphs. This time we are going to cover Hall's theorem, also known as Hall's marriage theorem, which is about bipartite matchings again, and it's how you determine when a graph doesn't have a nice matching. So if we recall from last video, we had this bipartite graph. We ran our algorithm to find a maximum matching, and this is the matching we got. And we noticed even though there were 5 jobs and 5 applicants, no matter what we did, we found one job did not get filled. And so one question one can ask is why? Well, let's look at the job in question. It's job E. And so it's worth pointing out for this bipartition, I'm letting the top set be A, because we only care about filling the jobs. And we look at who applied to job E. 4 and 2. Now, why didn't 4 and 2 get job E? Well, because 4 had accepted job C and 2 had accepted job A. And now we see that if we look at just this particular subgraph with just those 3 jobs and those 2 applicants, we find a W graph. We find a bipartite graph. Well, plus an additional edge. But we see what the problem is. If we restrict our attention to just these jobs, for these 3 jobs, there are few applicants than positions. And if you have fewer applicants than positions, you can't possibly fill them all, right? Because once you fill the first couple, the last job ends up having no one left. And this leads us to the precise statement of Hall's condition. Hall's condition states that for every subset of A in your bipartite graph, the size of the neighborhood of S is at least A, where the neighborhood of S are the set of vertices in B that are adjacent to A. So it's an edge for some A in A. Of course, if you don't like this abstract set theory definition, the idea is simple. What you're saying is that for any subset of jobs, there are more applicants who applied to those specific jobs than there are jobs. Because as we saw, if you don't have this condition, you run into a problem that there's more jobs available than there are people to work with, and then you end up with a labor shortage, like we currently have in our country with labor jobs. So you need qualified technicians, you need qualified applicants, you need to find a nice matching. In other words, we need Hall's condition to be true for a bipartite graph. If you want to fill every position, this has to be true, or else you can't do it. Now we mention one of the most famous theorems in graph theory. Given a bipartite graph with 2 partition sets A and B, so you've got vertices in A and vertices in B and edges going across, but nothing else. Then there's a max. You can find a matching where for every vertex in A is incident to an edge in the matching, if and only if G satisfies Hall's condition. In other words, either every job is going to be filled, or there's going to be a specific subset of jobs where you can actually show your employer, look, there were too few applicants for these jobs, there's no way to fill them all simultaneously. And that's often how Hall's theorem is applied in practice. It's usually been extended where you consider edge weights or preferences and things like that, where the goal is to find some sort of matching where everyone is happy. But this is a first step in that direction. Just that every job can be filled is progress. In particular, now given a bipartite graph, you could try to find a maximum matching that matches every element in a set A by doing the algorithm from last time, finding alternating paths and augmenting paths and swapping the edges on the path. And when you end that algorithm, if you end up with something that's not a matching that matches everything in A, then you know by this theorem that you should be able to find a subset that has a small neighborhood. So as an example, let's consider these 2 different bipartite graphs. One on the left with vertices A, B, C, 1, 2, 3, 4, and one on the right with D, E, F, G, and 5, 6, 7, 8. Note these are actually being regarded as separate graphs. Now let's try finding matchings. And so for this A the set I want to match is the set on top. Can I find a matching such that all the A, B, and C are each involved in the matching? Well, let's try it. I see that I should be able to match 1 with B, and then 2 with A, and then 3 with C, and voila, there's a matching with size 3. It's clearly the largest matching you can get because the number of vertices in A is 3, and so everyone in A is happy. All the jobs were filled. Now I turn my attention to the second graph. I see G has degree 1, so let's go ahead and match him with his only neighbor. Since that's the only person that applied for that job, that one has to get the job. And now we immediately see a problem. Job F can't be filled because the only person that applied for job F was 6, and he's already got a job. And so now we see that here is our counterexample, that the set A, S, equals FG creates a problem because the neighborhood of S is just the vertex 6, and so that the neighborhood has size 1, but the original set has size 2, and if 2 jobs have only 1 applicant, they can't both be filled. And so that's what we do. You either find a matching, or as you run the algorithm, you find a subset that violates Hall's condition. So now this isn't relevant for homework, but for historical reasons I should include the original application of Hall's theorem. Actually, Hall was studying set theory. His problem was that he was given a bunch of collections of subsets, and he wanted to find distinct representatives, so a way to circle elements of the set, such that there's a particular one in each set, and despite my mistake, he was actually perfectly okay with something lying in an intersection if you wanted to, as long as you indicated which set he belonged to. So these are called distinct representatives. They're supposed to represent the set they belong to. You know, it's similar to like an electoral college. Each electoral district has to elect a member from that district. And the way Hall's marriage theorem is understood now, and the way we solve his original problem, is we make the following bipartite graph. The bipartite graph consists of the set, the numbers one part consists of the numbers 1 through n, indicating the sets from your collection. The other set is just the elements. And then you have edges whenever one element is in one set. And so for instance, suppose this was A1 and this is a point X. In my graph, I'd expect to find an edge between X and 1 because X is in 1. Likewise, over here, this guy right here, Z, is in 1, he's in set 2, and he's in set 3. And so then it turns out solving Hall's problem is equivalent to finding a bipartite matching in this graph. A bipartite matching is a selection of edges, and so you're getting each subset, each set in your collections appearing once, and you're picking the representative by using the edges. So for instance, if our matching used 1 and X, then that would tell us that X would be the representative for A1. And so from this, Hall's condition states that for all S contained in the numbers 1 through n, you need the sizes of the set to be bigger than or equal to the size of the set. That's what the neighborhood condition turns into. That's the original condition Hall introduced. And of course, I should also mention some other extensions. Hold on. So now I state some other extensions of the marriage theorem, most of which we will not cover. But it's worth noting that a lot has been done in this area. One constant application is where you're interested in minimizing cost. You want to get a bunch of, or maximizing profit. You got a bunch of tasks. They each cost a certain amount. You want to get every job done, but you want to make the maximum amount you can. And so those interested, it's called the Hungarian algorithm. And so this is talking about matchings where each of the edges has some kind of weight. Another common one is called the Gale-Shapley algorithm, stable marriage theorem. So here you have a bipartite graph, and for every boy, he's got a ranking of the girls. For every girl, she's got a ranking of the boys. And the thing you want to get is you want to set it up so that if boy B marries girl G, and boy B prime marries girl G prime, then it shouldn't be the case that G prefers B prime and B prime prefers G. Because then, of course, the idea is that's not a stable marriage, because one of these marriages they will break off and commit adultery. This stable marriage algorithm actually is used in the medical field. This is actually the algorithm they use to assign residents to hospitals. The residents, after they get their medical degree, rank the hospitals they're accepted to, and the hospitals rank the residents, and then they run the computer program, and it decides who's going to move to where. The other final one is Tut's theorem. This has to do with matchings in general graphs. And it's a much more complicated condition, but it turns out there is another condition that's necessary and sufficient to guarantee that you have a matching where every vertex is matched in a general graph. And so obviously it would fail for the 5 cycle, but it's nice to know such theorems exist. The proof of that theorem is highly non-trivial, so I would not give it in this course anyways. That's really all I have to say about Hall's marriage theorem. It's actually a very, very famous theorem in graph theory, and it's got lots and lots of applications in the real world, and it's got lots of applications in graph theory itself.